Okay, so I'm now going to finish up our discussions of surface integrals with talking about heat flow. And this is discovered by Fourier, and this is called Fourier's law. And the law, it says that, I'm going to be very casual again with the notation, heat prime of T, the change in the derivative of heat with respect to T of some region, is actually equal to the temperature gradient, surface integral of a temperature gradient. And I'm actually going to draw this in 1D. I think it's a lot more clear what's going on with it when you draw a temperature. So our region is going to be just this line interval, and U of x will be the temperature. And so that means the temperature gradient will be the derivative. Okay, so what I'm going to talk about in this video is why this is true, but I'm going to do it kind of a rough way, but it'll help tell you. You'll get some intuition, I hope. So I think you might know the second law of thermodynamics. And this roughly says that heat flows from high temperature to low temperature. And there's no flow if the temperatures are equal. Right? And you can burn your fingers on a hot stove, but not from a handshake. I won't get into hot humans in this video. So the point is that a temperature difference causes heat flow. So let's go back to our diagram of this parabola that I drew, because that's a good illustration of how it's heat flow. And if we look at this boundary point, I'm just gonna zoom in, if you don't mind. So let's call this B, let's call this A. So if U of B, if this is big and U of A is small, there's actually going to be heat flow to the left. Right? So if we now let A approach B, what this is really saying is that U prime of x, if that thing is positive, that implies leftward heat flow. Okay? And if we go back to the other side of that parabola, and I'm going to zoom in really quickly, what this is saying is that if U prime of x is less than 0, that implies rightward heat flow. Okay? So in this configuration, we see there is a heat inflow. So in other words, heat prime of T is positive. And what else is positive? The only other positive things we have are U prime of x at the right spot and we have negative u prime of x at the left spot. Remember, negative on the left spot, that signifies positive heat flow. So that means u prime of x on the left should be, we're going to put a minus sign to get a positive thing. So in general, whenever you see a bunch of positive things, there's going to be a relationship. So the heat prime of t is actually going to be proportional to u prime of x on the right side plus u prime of x on the left side. So in other words, it's the sum of the heat flows. Oh, I'm sorry, I just dropped my negative sign. There we go. Sum of the heat flows. Okay, so to get this into a surface integral form, we're going to now introduce the normal vector that we want. So the normal vector is actually just going to be a plus or minus sign. Because we're actually, remember, we're in x is a 1D. We're just in the 1D scenario. So the normal vector let me just draw the normal vectors really quickly. So at this stage, the normal vector just points to the right. Remember, our region is just this interval, and the normal vector points to the left over here. So here's n at the right side, and here's n at the left side. So it's just a plus sign, and this is just a negative sign. So actually, u prime at r, it's actually equal to the gradient of u dotted a plus sign, because the gradient of u is just u prime of x. In the single component there is. And similarly, negative u prime on the left side, it's that negative one dotted with u prime of x. So it's actually equal to the normal vector dotted with the gradient of u. So my point with this is that the negative sign corresponds to the left normal vector. Okay, so in other words, n dot gradient u this is now the heat flow. So it's a sum over n dot gradient u. And it's a sum over on the boundary of our interval. The boundary, namely the left points and the right point. And so now if we upgrade x to 3D, then really it's just the same thing, right? So now the heat flow rate is actually just going to be, again, a sum over the normal vectors on the boundary of our region. Our region will be some 3D, our 3D region, and our region of integration now will be the boundary, that is S. And this, of course, is just gradient u dot d vector S in our notation. And what I'm going to do now to complete Foyer's law is I'm going to put a k here. And because in physics we always need the we need the units to match up, so the k will just be chosen for units. and for our discussion, it's irrelevant. Okay, so the reason I presented this is because this is sufficiently simple that I think you could actually, I don't think you even need paper if you think about this. You can actually just kind of visualize what's going on in your mind, and that'll help you see why we're using a gradient. The whole discussion here is to say, why is this a gradient U? And I hope this helped you. Thanks for watching.